Tonight what we're going to be talking about are ionic and net ionic equations. And the whole point of them is to look at what those ions are doing, and that's where the ionic comes from. And the net ionic equation is where it shows you what exactly during a chemical reaction is changing during that reaction. Because even though things combine with other things, they're not necessarily actually changing. And so what you're doing from the ionic to the net ionic is you're getting rid of all of those things that actually don't change. So let's do a few problems and understand it. So this is for net ionic equation. Normally what you see is something like this formula, okay? And we have parentheses there, even though for the nitrates and stuff like that, even though you don't need them. And typically you wouldn't write them. We're showing you them because they'll come into play later. But what you want to notice is that these are all aqueous, okay? Here's a solid, and then this guy is aqueous. What it looks like when you're looking at this equation is that AgNO3 is combined, NaCl is bonded together, AgCl is bonded together, and NaNO3 is actually literally bonded together. But when you're in an aqueous solution, as we've already learned during the solutions or the intro to solutions unit, these aqueous solutions, these ions are actually not bonded or touching one another, okay? Instead, they are dissociated and separate from one another. So for example, NaCl, as it's written, if this was my beaker, Na would look like it was bonded to Cl. But in actuality, what's happening in water is they separate, and you have your Nas completely separated from your Cls. Okay, so this is the true one, even though with this format, it looks like they are literally touching and bonded. So what you want to do for this is called the molecular equation. It's the one where, it's the one where we're dealing with the molecules, what molecules are involved in it, okay? An ionic equation shows you what the ions are doing. And how do you do this? How do you transfer this to this? First, you are only going to focus on your aqueous solutions. So everything that's a solid, liquid, or gas will remain the exact same. So when we look at this, if you look at the beginning for the molecular and you go down to your ionic, which is this guy down here, you will notice that your solids have not changed at all. The only ones that will change in this whole process will be your aqueous solutions. Why? Because as an aqueous solution, they are separated into the ions when they are in a water solution. So they're literally separated. So the difference between this molecular and the ionic is that you're separating the ions as they would look in a solution. Okay, so what you do is you first do your elements separated of all your ionic or your aqueous solutions. Okay, notice I did Na, NO3, yada, yada, yada. The next thing you want to do is give them their amount. Okay, in front of it is a big coefficient. So in this case, every single one, you only have one. So instead of writing the one as your coefficient, you just ignore it and you don't write anything. And then the last one that you're going to do is you're going to write their charges. So what is Ag's charge? What is NO3's charge? What is Na's charge when it is as an aqueous solution? Na's charge, and then NO3's. Okay, so I call this the BAC method. What does B stand for? Break them up. So you break up your cations from your anions. A, give them their amounts. And then C, give them their charges. Once again, this only applies to aqueous solutions. This guy right here is your ionic equation. Now to get net ionic equation, which is the idea that what they want to do is just show, hey, in this equation, these are the only things that are changing, okay, from the reactant side to the product side. So what you do between the ionic and the net ionic is you get rid of these spectator ions. Well, what is a spectator? All they're doing is watching the actual game, right? So that's what they're doing in the chemical reaction as a spectator ion. They're actually not involved in the reaction. They're just kind of along for the ride and watching it. So if you look at this and try to look away from the red marks, what you'll notice is that this was the exact same thing as your ionic equation. Now when I cross off, the things that are on the exact same as on the left as on the right. So NO3 minus 1. I've got that on the left. I have an NO3 minus 1 on the right. Notice that they are the exact same amount, and they have the exact same state, and they are the exact same charge. Okay, Na plus, it is on the left as Na plus aqueous, and it is on the right as Na plus aqueous. So I can cross that off. If I look at the left for Ag plus, notice that there is no Ag plus on the right-hand side, so as written by Ag plus. So therefore I would keep it. Cl minus aqueous, there is one on the left, but there is none of those on the right, so I can't cross that out. What you'll notice about when you have a double replacement reaction is that whatever formed your solid is going to be the ions that are left in your net ionic equation. Okay. All right, so this would be the ones that you would be left with for your net ionic equation, where you got rid of all of your spectator ions. So here's another example of a net ionic equation. Here's your general format up here, but here's a more specific one. So what you're going to do is you're going to break them up. Okay, so you got your Ba, you got your Cl, Mg, SO4. Okay, do the exact same thing to the other side. BaSO4 though on this side is a solid, so that's why they didn't do anything with that. Okay, then give them their amount. So I follow the B, now I need to do the amounts. For Ba I only have 1, that's why I don't have anything as a coefficient. Cl I have 2, so it becomes a 2 in front. Mg I have 1, and SO4 I have 1. On the right hand side I have Mg as a 1, and then Cl I have 2. So I gave them their amounts. Now give them their charges. That's where you get the +2, the -1, +2, -2. Leave that guy alone, +2 and -1. All right, now if I wanted to get rid of all of these and do my spectator, get rid of the spectator ions, I'm going to look at the left. I have a Ba +2. I do not have a Ba +2 on the right, so I leave that. I have a 2Cl minus aqueous. I have a 2Cl minus aqueous, so I'm going to get rid of that. That is a spectator. I've got an Mg +2 on that. I've got an Mg +2 on the right. I have an SO4 -2 on the left. I do not have an SO4 -2 on the right. So if I looked at this, my net ionic equation, because this is a double replacement reaction, would just form whatever my solid was. So notice I end up with Ba plus SO4, and then I end up with BaSO4. All right, so let's try this one on our own. Okay, so here's my molecular equation. So we've got my molecular equation. Okay, now we're going to do ionic. So we need to follow that BAC method. So I'm going to break them up. So I got NH4 and then plus Cl. Okay, you should write AQ after all of these. Plus, I've got Hg, so I'm going to do Hg, plus C2H3O2 goes to, I've got, oh, that's not right, that should be NH4. I've got NH4. These all need aqueous written after them. Okay, and then plus my acetate, H3O2. Aqueous, and then notice that this mercury is, the mercury chloride is the same, so I'm just going to leave it, because it is a solid, I'm going to leave it as is. All right, now I broke them apart. Now I need to give them their amounts. In the first one I have 2 NH4s. I also have 2 Cls, because that 2 is going to distribute. I have 2 Hgs and 2 acetates. I have 2 NH4s and then also 2 acetates on the right. Okay, and nothing once again with this mercury 1 chloride. All right, the next thing that we're going to do is we're going to give them their charges. We've got a +1, a -1, a +1, it's 2, yeah, +1, and then a -1. And then we've got a +1 and a -1. So I've did my B, break them apart, give them their amounts, give them their charges. All right, now I'm ready to cross out the ones that are my spectator ions. So this would be my complete ionic equation. Now I need to do my net ionic. Okay, and then we get to cross off the ones that are exactly the same on both sides, which would be your acetate and your ammonia. And then so we end up with 2Cl minus plus 2Hg plus goes to Hg2Cl 2. Now, a way to check is that your charges on both sides have to be the same. So I have a -2 from these two chlorides, I have a +2 from the mercury, and I have a 0 overall charge on the right side. So +2 and a -2 makes it equal to 0. So I have a 0 on the left, I have a 0 on the right. As far as amounts, I have 2 chlorides, 2 mercuries. I have 2 mercuries, 2 chlorides. So my amounts are the same, everything's balanced, so I know that this is a proper net ionic equation. All right, now what I want to do is just come up with an easy one of why those double replacements when you didn't produce a solid led to no reaction. Okay, so we're going to do NaNO3 plus KC2H3O2. Okay, and these are both going to be aqueous solutions. When they do a double replacement, we'll be ending up with KNO3. They all have 1 or -1 charges. That would be aqueous if you look at your solubility chart. And then NaC2H3O2, that also is aqueous. So this is my balanced molecular equation. Now I'm ready to do my ionic. When I look at my ionic, once again, we're going to separate, we're going to break apart. So we get Na plus NO3. Remember, you're only breaking apart the ones that are aqueous. C2H3O2 goes to K plus NO3 plus Na plus C2H3O2. Okay, and then you want to write aqueous after every single one. AQ, AQ, AQ. Takes a little bit. All right. Now I broke them apart. I gave them their amounts. They were all 1s. Now I'm going to deal with my charges. +1 minus, plus, minus, plus, minus, plus, minus. All right. Now this is my ionic equation. Everything seems to be floating around. There were no solids, no liquids, no gases, so everything's separated. And I use my BAC method for absolutely everything between my molecular and my ionic. Now I'm ready to do my net ionic. Remember, net ionic, you get rid of all those spectator ions or the ions that are not involved in anything. So I've got an Na plus on the left. I have an Na plus on the right. I have an NO3 on the left. I have an NO3 minus on the right. I have a K plus on the left. I have a K plus on the right. I have a C2H3O2 minus on the left. I have a C2H3O minus on the right. So now if I want to write down everything that I didn't cross off, I would have nothing on the left and nothing on the right. So notice that for your net ionic equation for a double replacement reaction where we would write no reaction, you end up with nothing that changed. We started with everything and we ended with the exact same things. Whereas with the other ones, we've at least produced a solid. They changed what their state looks like while they are in an aqueous solution. These guys didn't, and because of that, that is why we end up writing no reaction for things where a double replacement has 2 aqueous solutions. All right, hopefully you have an understanding more of why we have double replacement reactions with 2 aqueous solutions and no reactions for those. Also understand that lovely BAC method for when you are trying to do your molecular to your ionic and get rid of all your spectators and ions to go from ionic to net ionic. Have a great evening.